Hello everyone and welcome to this module. In this lesson, we are going to learn about how our bodies interact with the environment to manage temperature and the crucial role clothing plays in this. Our bodies are constantly making tiny adjustments to keep our internal temperature just right. Think about it. When you're exercising, your metabolic rate kicks up, generating more heat. To deal with that, you start sweating, allowing your body to dissipate that extra heat and avoid overheating. The external environment plays a massive role here, influencing the various transport phenomena in thermoregulation. Let's take a closer look at the general heat balance equation, which is quite intuitive. Simply, on the left side, we have heat gains, and on the right side, we have heat losses and storage. Here's a breakdown of what each term means. M stands for metabolic heat production. This is the heat our bodies generate simply by being alive and carrying out metabolic processes. W represents the work done on the environment, like running, cycling, swimming. On the right side, we have K as the conduction term, which is heat transferred when you directly touch something. C is the convective term, in most cases air moving around your body. R is the radiative terms. Our body constantly absorbs and emits heat through radiation. ESK is the evaporative heat loss from the skin, primarily through the evaporation of sweat from the skin. CRES and ERES are the convective and evaporative heat losses from respiration. And then we have the term S that represents the body heat storage. If S is positive, you are storing heat and getting warmer. If it is negative, you are losing heat and getting cooler. Now, let's introduce the role of clothing. Clothing impacts our heat balance by reducing the convective, the radiative, and the evaporative heat loss. These effects are achieved by garment properties such as insulation, air permeability, moisture management, and the ability to absorb or reflect radiation. The level of insulation of a garment refers to a material's resistance to conduct heat. The more insulating a garment is, the better it traps heat close to the body. As you can see in the graph, RCT, the thermal resistance, is closely related to the thickness of the material. The thicker the garment is, generally, the higher its thermal resistance is, meaning it's better at insulating. However, insulation isn't just about material thickness. It also depends on the trapped air within the fibers and layers, since air is a very good insulator. Finally, let's look at the concept of permeability. Permeability is key for water and wind protection. The diagram illustrates what happens as permeability decreases, moving from the left to the right. In a highly permeable garment, on the left, both water vapor, by blue arrows, and air, red arrows, can easily pass through the fabric. This allows for a good breathability but offers less protection against wind and rain. As permeability decreases, middle and right panels, the garment becomes more resistant to air and water vapor. However, if the garment is too impermeable, like a fully waterproof, non-breathable rain jacket, it can trap moisture from sweat inside, leading to condensation. This can then make the skin or inner layer of clothing wet, reducing insulation and leading to discomfort. Now, let's bring in a practical and standardized tool for quantifying the clothing needed for comfort and safety in different environments, the required clothing insulation, or IREC. This specifies the necessary insulation to maintain a state of thermal comfort under various environmental conditions and levels of physical activity. IREC, which is expressed in cloth, serves several key purposes. It acts as a measure for cold stress. Indeed, a higher IREC value means more insulation is needed. It provides an analysis of the effect of the environment on the human body. And finally, it's a valuable tool for prototyping and studying the effect of different clothing on thermoregulation. IREC is defined by the formula shown, where the numerator is the difference between the temperature on the skin and the external clothing temperature. The larger is the difference, the more heat is transferred. The denominator represents the dry heat exchanged from the clothing to the environment. Essentially, the IREC formula calculates the thermal resistance needed for it to maintain thermal balance. Two different definitions of IREC are used. IREC neutral is the insulation required for thermoneutrality. This means the amount of clothing insulation needed for a person to feel perfectly comfortable. IREC minimum is the minimum insulation required for thermal equilibrium. This is a crucial safety threshold, indicating the absolute minimum insulation needed to prevent progressive body cooling and the onset of hypothermia. Here, we can see a practical application of the definition of IREC. We have three different zones: warm, neutral, and cold. In the warm zone, the clothing insulation, ICL, is higher than the IREC neutral, and this leads to an overheating zone. Your body will struggle to dissipate excess heat, potentially leading to discomfort, sweating, and, if prolonged, a risk of heat stress. In the neutral zone, the insulation worn is higher than IREC minimum, but lower than IREC neutral, and this carries to the regulatory zone, where your body can easily maintain thermal equilibrium. In the cold zone, the insulation worn is even lower than the minimum volume of IREC, and this means that we are in the cooling zone. In this case, your body will continuously lose more heat than the produced one, leading to risk of hypothermia if not addressed. But how do we evaluate the level of insulation? This is where the thermal mannequin test comes into play. Let's look at the setup. As you can see, a thermal mannequin is a life-sized, human-shaped dummy. What makes it thermal is that its surface is equipped with heaters and sensors, typically divided into 15 independent thermal zones. The mannequin is placed inside a climatic chamber, and this chamber allows for a precise control of environmental parameters such as temperature, wind speed, and relative humidity. The formula is used to calculate the clothing insulation for a specific zone on the mannequin. The numerator is composed by the temperature difference between the mannequin and the environment times the area of the considered zone in square meters. The denominator is the heat flux required to keep the temperature fixed at 34 degrees by the heater. By measuring how much heat is needed, this standard allows us to calculate the clothing insulation. This concludes our module on energy balance. In the next module, we'll take a closer look at technical textile and the crucial role of moisture management.